According to collision theory, our young Earth experienced a massive encounter with a protoplanet named Theia about 4.5 billion years ago, and the outcome was nothing short of extraordinary. The violent impact hurled vast amounts of material into space, which gradually gathered in Earth's orbit and, over time, became the Moon. In today's discussion, we'll explore the evidence that supports this remarkable theory, imagine what Theia might have looked like, and reveal why parts of this ancient world may still be hidden deep within our planet. Earth and the Moon share a dramatic history, shaped by chaos and transformation. Sometimes, it takes a catastrophic event to bring something entirely new into existence. While the Moon's exact origin is still not proven with absolute certainty, the most widely accepted explanation is that our ever-present lunar companion emerged from the debris of a colossal collision. As scientists suggest, Earth and Theia didn't crash head-on. Instead, the impact occurred at an angle, causing much of Theia and parts of Earth's crust and mantle to vaporize. This material later condensed in orbit, where gravity pulled it together, eventually forming the Moon we see today. But how can we know this today? The answer lies in studying the composition of both celestial bodies, specifically, the isotopic makeup of Earth's mantle and the Moon's rocks. If the giant impact theory is correct, our lunar companion should be made up of roughly 70% material from Theia. Since each body formed in different regions of the primordial solar cloud, their rocks should contain varying proportions of certain isotopes. However, earlier research told a different story. Analyses of lunar meteorites and moon rock consistently revealed an extremely high similarity to Earth's composition. That shouldn't happen if the Moon is primarily made of Theia's remnants. Then, in 2014, scientists from the University of Cologne uncovered a key clue that revived interest in the Theia hypothesis. They examined basalt samples from 3 Apollo missions, samples that had been stored virtually untouched in NASA's secure facilities. After carefully releasing the oxygen from the rocks, cleaning it, and analyzing it with a gas mass spectrometer, they detected, for the first time, a tiny difference in the ratio of the rare oxygen isotope O17 to the common isotope O16. The difference was extremely small and challenging to measure, but it served as the first solid evidence that another celestial body, in addition to Earth, played a role in the Moon's formation. So, why are Earth's and the Moon's isotopic composition still so alike? Researchers are currently debating 2 main possibilities. The first theory proposes that our young Earth had an extremely icy encounter, with Theia being composed largely of ice. The second theory assumes that the collision partner formed at roughly the same distance from the Sun as the proto-Earth and, because of this proximity, was also made mostly of silicates. This shared origin would not only explain their chemical similarities but could also clarify why the 2 celestial bodies eventually collided. But what exactly did Theia look like? It's no coincidence that this hypothetical protoplanet is called Theia, a name first introduced in a 2000 scientific paper. In Greek mythology, Theia is the mother of Selene, the moon goddess. If the planetary counterpart of this mythological figure truly existed, it naturally sparks many fundamental questions. What kind of world was Theia? How large was it? What was its appearance? And could it have supported life? Of course, since Theia remains a purely hypothetical protoplanet that has never been directly observed, we cannot answer these questions with complete certainty. Interestingly, and this is where things get exciting, scientists can make an educated guess about Earth's ancient collision partner by using scientific models and comparing it to other known celestial bodies. According to the collision theory, researchers believe that Theia was roughly the size of Mars, with a diameter likely between 6,000 and 7,000 kilometers. For perspective, Earth's diameter is over 12,700 kilometers, meaning Theia was significantly smaller than our planet. Despite its smaller size, this protoplanet still had enough mass to form a roughly spherical shape. As for its surface, it's thought that, Much like the young Earth, it was coated in volcanic rock. Since early solar system bodies were frequently battered by impacts, Theia likely bore a rugged landscape marked with countless craters. It's important to remember that Theia wasn't unique. Scientists suspect that hundreds, perhaps even thousands, of protoplanets once orbited near our world. After the Sun formed, the accretion phase began, a period when dust and gas surrounding our young star gradually clumped together. First came planetesimals, then protoplanets, and finally, fully formed planets. Over time, these protoplanets either merged into larger worlds through collisions, were shattered and destroyed, plunged into the Sun, or were flung out of the solar system entirely. How many potential worlds were lost in this cosmic shuffle? No one knows for sure. But one thing is certain, life can only emerge if a planet has the right kind of atmosphere. If Theia had an atmosphere at all, it was likely very thin, composed mainly of volcanic gases such as carbon dioxide, sulfur dioxide, and water vapor, much like the early atmospheres of Earth or Venus. However, this atmosphere would have been completely stripped away during the violent collision with Earth. But what if that collision had never happened? Could Theia have supported life? This question applies not just to Theia, but to Earth as well. Without the impact, there would be no moon, meaning Earth's axial tilt would be far less stable, leading to a chaotic climate. Tides would be much weaker, reducing the creation of coastal zones that were ideal for early life. A different daylight cycle would also have altered the planet's biological conditions. While life on Earth might still have been possible, it would have evolved under far more extreme and unstable circumstances. As for Theia's own habitability without the collision, that's a separate question. In theory, it could have been possible, but the odds were slim. With a size comparable to Mars, Theia would have been large enough to hold onto an atmosphere and maintain geological activity. However, its close orbit to Earth likely meant that, sooner or later, it would have lost the gravitational tug-of-war and been ejected from the solar system entirely. Beyond this point, we can't be certain whether Theia ever held water, especially since it formed in the inner solar system, where volatile compounds like water struggled to condense. Yet, if both Theia and Earth emerged from the same region, why does our planet hold such abundant, cool water? Scientists believe that Earth didn't acquire all of its water from local sources. Instead, a portion likely arrived later, delivered through a combination of different origins. Beyond the water locked within minerals, much of Earth's supply likely came from water-rich planetesimals that bombarded our planet, delivering the precious elixir of life. Some theories even propose that Theia itself carried water, depositing it on Earth during its catastrophic collision. However, because Theia was smaller than Earth, it would have lost its atmosphere, and with it, its water, relatively quickly, even without the impact. Factors such as the relentless solar wind would have stripped it bare. Without protective mechanisms and with an unstable orbit, Theia would have struggled to hold on to its water, making it unlikely to have been a long-term habitable world. But what became of Theia after the collision? According to prevailing theories, much of the debris thrown into space coalesced to form the Moon. Still, was Theia completely obliterated? Not exactly. Recent findings hint that Theia might still be here, quite literally. Experts believe that most of Theia's dense core elements ended up within the Moon's own core. The fate of its mantle, however, remains a matter of debate. Some scientists suggest that fragments of Theia's mantle may still lie buried deep within Earth's own mantle. Supporting this theory are two colossal anomalies in the lower mantle, each roughly twice the size of the Moon. These so-called large low-velocity provinces are found deep beneath the Pacific Ocean and Africa, and are known for dramatically slowing down seismic waves. This suggests that the mantle material in these regions could be unusually hot, soft, and compositionally different from the surrounding mantle. Some scientists theorize that these anomalies might not be native to Earth at all, but rather remnants of the ancient protoplanet Theia. According to the prevailing view until recently, any remains of Theia were believed to have been completely broken down and blended into Earth's interior long ago through dynamic mantle convection. It was also unclear why Theia's remnants, if they existed, would have formed into two distinct, massive regions.